Okay, good morning. It's 11 a.m. on the East Coast, 8 a.m. on the West Coast. I'm Renee Phippen with Delve Underground. I'm co-chair of the DFI Tunneling and Underground Committee. My co-chair, Bob Steer with Drill Tech, is here as well. This is our first webinar that we are hosting, so we're excited to see how it goes. And we plan to host another one next year with the topic TBD. And with that, I'd like to go to the next slide. A few rules. During the webinar, all attendees are muted. The Q&A is following the presentation, and you must put your Q&A into the Q&A chat box, and we'll go through that after our speaker is done. And our speaker today is Jamie Schick. He is with Delve Underground, which is my company. I've worked with Jamie for a number of years, also on this project he's talking about. So I'm excited to have him talk. He's always engaging. He's a principal geologist here, and I'll let him say a little bit more about himself as well. Thank you.
Thanks, Renee. Good morning, everybody. So yeah, Jamie Schick. I've been with Delve for 13 years now. Prior to that, I worked for the Oregon Department of Transportation and then several other consulting firms that are no longer here today. My practice has mostly been in heavy civil, both underground and above ground infrastructure, tunnels, dams, roadways, geological hazards, and I'm excited to be here to talk about the Arizona In project. This is a project that I've been on and off involved with for many years. It's got a long history that I'll get into today. It's got a fascinating mitigation and some new mitigations that we'll be talking about today. So just a kind of an agenda for you. We're going to start with just a little bit of history. What happened in the 90s with the initial mitigation of this slide, some of the work that they did once they started seeing additional movement, and then get into a failure from January 23, talk about their initial response, and then what we've done since then with more additional mitigation out there. So just a reference for everybody, you can see on the left, we've got the Oregon coast. This is down near the California border. The site's on Highway 101 in a very remote part of the state. The central image gives you a sense of the general dimensions of this slide in red, and then as well over on the far right, just to get a bit of a sense of orientation. It's about a half mile long and about a third of a mile wide. So this slide's been active really since they built the road, in every 15 to 20 years. It's had some fairly substantial movements that have shut the road down. In the 1980s, they moved about 500,000 cubic yards off the top, trying to unload the landslide. Which again slowed, but again it failed in 1993, which precipitated a major mitigation, and then of course the January failure last year that we'll be talking about today. So why do we care so much about this landslide? It is in a relatively remote area, and the consequence is that there's no good way to move north-south when the road is closed. So you can see the blue line shows sort of the direct path, and then the detours that add 3 or 4 hours to the route. And there's just not a great ways to get around that, and a lot of that is really driven by the rural nature and also the geology of the site. So this is really, the site's located kind of at the northern extension of what maybe folks from California are more familiar with. It's known as the Franciscan Formation. So it's a sort of a metasedimentary rock that has been intensely sheared and deformed over time due to the forces of being accreted to the North American coast. You can see down on the lower right, it's basically a wedge of material that got caught between the two plates and just like a blender ground up and intensely folded and sheared as that plate was being subducted under North America. So you can get a couple of examples of this. Some of these are photographs from California as well as from Oregon. Just looking at the intensely deformed nature of this. So this was at one time, this was nicely layered sandstone siltstone material and has since been completely obliterated from a structural standpoint. This kind of fine scale view of it from a hand sample. You can see all the small class of gravel beds and sandstone in this clay siltstone matrix. There's another sample. These are all samples from the project that we collected last year. And just one more example of the kind of material that we're pulling out of the ground. So this is another view. This is a hillshade image of the site. And what really stands out, we're really talking about what's also known as a block and matrix material. So blocks of material in a fine grain or mixed material matrix. And the scale of this goes from, a hand sample that you just saw to huge blocks. This is actually the arrows are pointing to large blocks that are in a even larger landslide that is slowly moving towards the Oregon coast. And rafting along in those are blocks on the order of, 1,000-foot thick, 2,000-foot thick. So the scale is quite large here. And in fact, one of the largest ones that are on the site is this one right here. So this is actually a large block of sandstone that most likely prevented the landslide from actually moving further to the south. So some of the unusual parts about this is that the toe of the landslide has a very steep face and is being very actively eroded away by the ocean. And that's one of the challenges to the site and stabilization is that we keep losing the toe material, the buttressing material is being washed away. Access is extremely challenging. So, doing work on that face is very hard, if not impossible. So following the 1993 failure, the Oregon DOT decided that enough was enough, and they brought on Squire and Associates, who conducted a fairly in-depth inspection or investigation. The typical borings, inclinometers. They actually did pump tests to understand the hydrogeology better. Because of the issues with like putting a buttress in or anything along those lines. And ultimately did decide that drainage was a viable option. The images on the right are basically the horizontal drains that were installed above the highway. So the highway is kind of cutting through the middle here, like this. And these are all the drains that were installed above. They installed about 70,000 lineal feet of horizontal drains through a series of platforms that they built access roads to. To address the lower portion of the slide, they actually went and they installed drains through a shaft. So they built a 200-foot deep shaft, about 18 feet wide, in the middle of the landslide. Then they sent a work platform down and they drilled horizontal drains from 3 separate work platforms and put in about 30,000 feet of drains to try to dewater the landslide toe. So from a support standpoint, the original shaft had about 6 inches of shotcrete with lattice girders on a 3-foot center. There was a collar at the top. The structural engineers that I work with consider this a relatively, what they would say, skinny liner, but it did hold up it's actually still out there, at least parts of it now, and so it did do its job for close to 25 years. So in the sort of mid 2010s, they started seeing more deformation of the roadway. concerns about, what's going on. Is the system starting to, reactivate? There's also movement. There's a larger slide to the north. You can sort of see it. The whole thing is outlined in red. That's called Arizona North versus Arizona In. Whole site is called Arizona Landslide Complex. So they wanted to take a closer look at the whole site and try to understand what's going on out there, and were there other issues that they need to be concerned with. So one of the first tasks was to go out and install a larger network of borings, with instrumentation, so inclinometers and vibrating wire piezometers. So they put in an additional 8 boreholes spread across not just Arizona In, but also to the north, to try to get a better sense of what's going on out there. Are there areas that they haven't done anything that they need to be concerned with? They also started using INSAR, and that, no surprise, the red is moving and green is not, and for the most part, the area that had been previously mapped was also the area that continued to show gradual creep across the site. It's the system, in the Oregon coast, it's quite a wet part of the country in the wintertime, and that's really sort of shown with the graph on the right. You can see the accelerated movements really during the winter months, and then things sort of calm down during the summer months when it's typically drier. We were fortunate that there were several rounds of LiDAR that have been flown for the site. So this is change detection, basically taking one layer of, so LiDAR is a scanning technology that uses a laser to scan the ground surface and create a topographic rendering. If you do that more than once, you can compare the two to see if there's movement. Again, red is moving, and blue is actually sort of showing negative movement, or moving in. So there's a lot of scatter here, but you can certainly see at the toe a fair bit of activity, mostly probably related to coastal erosion processes. So, the conclusion was that, there's still movement going on, that no shock, that the landslide is more sensitive to terrain events. Toe erosion, as you saw in the last slide, the red area there, was a very active process and a major concern here, and that the current drainage system was not functioning as well as it had been. Those conclusions were verified in January 2023. This is an ODOT geotechnical engineer standing on the down-thrown side of the landslide on the north portion. It dropped about 25 feet and shut the road down. There's the approximate limit. So in this failure, not the entire historical landslide moved. It was really sort of a lower portion of the slide that had most of the slope movement. Relatively little movement occurred in the upper portion of the landslide. So it's always good to look back at these, and hindsight is 2020. So the two images here are the change detection and also the INSAR data on the right. And it's pretty obvious where most of the movement is occurring. I think that the little INSAR, the challenge to the technology is that if there's too much movement, it actually gets beyond the level of the instrumentation being able to monitor. And so, you're left with this, is that because there's nothing happening here, or there's a lot happening here? And obviously there was a lot. These shapes are quite match up quite well with the actual failure. So just a bit of a recount. The start of the 2023 year was a really wet start, and they started seeing movement really early in the year. It started getting moving even more. By day 8, they had up to 3 feet of offset. They were trying to keep the road open, and then early on the morning of the 9th, the entire road just failed out and shut the highway down. The red arrows are kind of showing the lateral scarp in the foreground, and you can see the lateral scarp in the background that we saw the picture of earlier with the guardrail. So initial response, people mobilized very quickly out there. They were worried about mobility, especially for emergency vehicles. Unfortunately, the hospitals on one side and the patients on the other. So you can see that they've built this one-way lane on the top. But several days into it, everybody sort of took a pause and realized that no one had looked at the shaft. And so they went out, they got a crane, and they lifted the top off the shaft and looked into it, and there was about 50 feet of water in the shaft. And the shaft was no longer 200 feet deep, it was 140 feet deep. So the landslide had indeed sheared the shaft and was now ponding water. This is a bit of a cartoon for what we believe has occurred. And you can see that this shaft was literally just sheared off 140 feet down. That precipitated mobilizing some pumps and starting to drain that shaft. Obviously, it's probably pushing water back into the landslide, so it's actually contributing to the water pressures in the slide mass now. So they need to get that water out, and that pumping has been ongoing since that failure. So part of the initial response was to reestablish instrumentation. Obviously, everything had been obliterated with that level of displacement. So they had added 14 additional boreholes across the landslide, both above and below at the lower portions. They were fully instrumented with vibrating water piezometers and slope inclinometers, just to start to reestablish an understanding of what was going on. That was started in late March and went through June of 2023. They also, assumed that all the horizontal drains were no longer functional or were severely damaged. So they initiated a replacement of the drainage system. So that started in May of 23 and went through the summer. That was quite a network. So they installed about 30,000 lineal feet of horizontal drain from a series of pads all the way up the upper portion. Again, the lower portion not being accessible because of the steep face on the downslope side. There we go. So, 39,000. You can see here the network that they're doing. So all the drains were connected to a system of piping. And they also established a fairly elaborate ditching system to try to, again, get the surface water off and not let it soak in. That was all piped and taken down to a little ravine on the south side of the landslide to drain out into the ocean. So at that point, ODOT recognized that they needed to deal with the lower portion of the slide, particularly because so much of the recent activity wasn't really being drained by the phase 1 system. So Delve Underground was retained by ODOT and asked to help them with the design of the shaft and the lower drainage system to kind of stabilize this landslide. So one of the first things that we did was, obviously site visits, and put together some ideas about what we might do there. The initial there were sort of three options that we came up with. ODOT directed us that drainage was what they wanted. Buttressing was really not on the table because of the logistics of getting on the coast, access, and as well a variety of permitting and environmental constraints for the project. So the first option was like, wow, gosh, could we just go back down and rehab the existing shaft? Maybe we deepen it. You might have to enlarge it a little bit, make the line air a little bit more robust. but that, you've already dug most of that hole. So the next option was to put one right next to it. So just step off, put a new shaft in, do a similar drainage array, sort of radiating out from that, but that still keeps you in the middle of the landslide. And then the third option was to go over to this bedrock outcrop, get off the landslide, and then drain from the side to try to preserve the shaft. So if there's future movement, you might lose your drains, but you still have the shaft, which is your most expensive piece of infrastructure. One of the other things we did very early on was, of course, go out and visit the site and do a site visit. The shaft showed visible signs of damage. Even from the surface, you could see that it was no longer round, and in some places, some of the lattice girders had popped out of the shotcrete or were sheared. We did a scan of this, so we took we got a laser scanner and we lowered it down the middle. Basically, the same scanning technologies used to scan manholes for sewer systems and water lines. And we got a great view of what's going on down in the shaft. And you can see the sort of sections. You can see the shears that have of the shaft that have occurred. There's one here, and then there's another one down here. The whole shaft is listing to the northwest. And then here you can see where we start from a relatively circular shaft near the surface to an increasingly deformed shaft with depth. So this is kind of some views of these two alternatives. We pretty quickly decided that, yeah, we're not going to use that shaft again. There's too much damage, too much of a challenge to try to get in there and rehab that, enlarge it, and make it the size that we need to get a drill rig in there. So the two options that we were left with was one, again, a shaft coming in from the center of the landslide, and then a shaft that would be installed over on the right from the side of the landslide. So that would be alternatives 2 and 3. Not going to go through all of these. No option is perfect. I think that getting the consensus was that there were some pretty substantial safety concerns associated with putting a shaft in the middle of an active landslide, that we can't tell you when and how much the slide might move. Challenges working in the wintertime with a partially completed shaft or a partially completed drainage system. So some fairly substantial logistical challenges for alternative 2. Alternative 3, obviously it's stable ground, so that's a huge benefit. You could go back in if you lost your drains and replace them, but the drains are much longer. So we're looking at drains that are upwards of 1,000 feet to get across this landslide. So it wasn't like there was a perfect solution for this, but ultimately we did decide to go with option 3, just from I think probably perhaps the most were you've saved your infrastructure from future movement, and B, the challenges of getting contractors to do something like that just seemed like a very steep challenge. So so we moved this shaft into what we thought was a very large sandstone block. So getting off the landslide, similar blocks you can see across the site. So the first work, obviously, we had no subsurface information there. So out goes the drill rig again to start drilling holes. We had visions. So the lower pictures on the in the lower left are geologists mapping the sandstone blocks. This block goes all the way down. The middle picture there is down at sea level. So the sandstone block goes all the way down to sea level. You can see it in the through cut at the roadway. So we had a variety of ideas of maybe a drainage gallery at the bottom or a short tunnel to improve access to get underneath the landslide and drill up. However, Mother Nature and block and matrix material don't always cooperate with the geological model that you put together. So these are some pictures of the core. Upper left, that's some of the sandstone material at the near surface, fairly broken up, but definitely competent rock. The material in the middle is a much less competent rock, is the classic melange with varying size of clasts and a silty matrix, siltstone matrix. You can see the cross section on the right. Basically, the shaft. This is the proposed shaft right here. We had three materials. We had landslide debris off to the north or to the left in this section. The melange is underneath the majority of the site. And then the sandstone is really just like a cap rock in this case. So essentially what we had was a very large sandstone block that was acting as probably a buttress, but didn't extend very far down at the road site. So again, a little bit more of a detailed geologic cross section. There was a fair bit of stability analysis obviously going on to sort of evaluate like what do we need to do? How much drainage do we think we need? You can see the two failure surfaces, the more shallow surface that sheared the shaft. That was the one that was more active and perhaps of greater concern, but you can't ignore that the whole thing is sitting in a much larger, more ancient landslide. So modeling results, this is the challenge of large landslide stabilization. They don't really like to be stabilized. They don't like to show you a nice factor of safety of improvement or percentage improvement. So the upper part of this table is the improvements. We were basically looking at how much groundwater drawdown do we think we need? How much do we think we can get for this landslide? And for the larger landslide, we're challenged to get much more than 10 to 15% improvement. We're hopeful that the lower portion of the landslide with maybe a 20-foot drawdown, we're getting a 20-25% improvement in overall stability. One of the benefits that we had for the project was that we did instrument prior, at least in some cases, instrumented prior to the installation of the horizontal drains. So we had an opportunity to sort of say, okay, what are the drains doing? How much benefit do we get out of this? And thus we can sort of look ahead and say, well, maybe if we put this much drainage in, we'll get this much drop in groundwater levels. So that's essentially what we are seeing on the left. Those graphs are sort of saying, okay, this is how much of a drop in water levels we saw as drains were installed. The graph on the right is basically, so frankly, not all drains responded. So there were definitely drains that did nothing, and then drains where we had substantially more drop in water levels. And we're taking from a big data standpoint, we got about an average of about 9 foot of drop for that 39,000 lineal feet of horizontal drains. So actually, just to close that on that. So essentially, what we did was look at this from the standpoint of drainage density from a surface area standpoint. And if we look at that and we're shooting for 20 foot of drawdown in the lower, particularly in the lower portion of the landslide, that came up with about 60 to 65,000 lineal feet of horizontal drains that need to be installed. So what does that look like? So that's essentially, these are some of the typical cross sections that we put together for the drawing plan set. So you can see here in the upper left, there's a shaft on the right side right here, and then we're essentially installing drains rating out at 13 different levels. We stopped at about 50 foot below ground surface. That seemed to be about where we would have been punching drains into ground that wasn't saturated. You can see a typical plan view down here. We've got drains radiating out. The number of drains per individual level vary depending on the geometry of the landslide. The plans basically show a table with drains, azimuth, inclination, and length, so that the contractor can basically go to a certain level and know exactly what they need to install as they get into it. So just a little more of a cool view of 3D rendering. We did use, we basically built a model in Revit and modeled the drains. We built a model of the surface of the landslide underground, and used that to sort of help us guide where we needed to extend these drains to, or where we could stop. And then, for sure, some of these drains will hit the old shaft, even though we've worked very hard to try to avoid that. So what is this going to look like? We're basically looking at, one sec. Okay. From a sequencing standpoint, what this will be using basically ring beams and shotcrete from a stabilization standpoint. And so what happens is after we've got a collar constructed, we'll excavate down 4 to 5 feet, install another ring beam, put in some temporary shotcrete, and then continue down with the next level of excavation and another ring beam. So that's the first round right here. And then we'll continue down about 20 feet, I believe is what we've called out in the plans. And then you have to come back and install final liner before you go any further. And then continue on all the way down to the bottom. Following completion of the shaft, the idea will be to install outlet drains to the ocean. Obviously, if we're bringing the water in, it's got to go somewhere. So there'll be drains going out to the ocean that will be installed. We're also going to have drains from the existing shaft to the new shaft. So the existing shaft is still doing some good. So we'll add drainage that goes from that shaft, come back to the new shaft, and then out to the ocean. This is a little more detailed view of the lining system. You can see the ring beams here in section, basically an H-pile turned into a ring. They'll be in quarters, so prefab, lowered down, bolted together in place, and then shotcrete installed. There'll be one set of rebar that'll go in on the inside of that, and then we'll also have a collar at the top that will start the whole process off. So this is just an image of the shaft going down, and you can see the workers down there. So we anticipate this to be predominantly mechanical excavation. The sandstone will be a little bit more difficult to excavate, but the majority of this shaft is going to be excavated through the melange. So there will certainly be some larger sandstone clasts to be dealt with, but we anticipate mechanical excavation for all that work. So I'm a little ahead of schedule. Apologize for that, folks, but right now we're looking at bidding out. It's actually out to bid as we speak today. It's going to be probably notice to proceed in early 2025, with construction starting in early mid to late spring. We anticipate this to be shaft constructions for a good share of next year, and then the drains going in, the outlet drains going in, and then the horizontal drains. That'll be a fairly major part of the construction project. Obviously, 65,000 lineal feet of drain is not a trivial task, but hopefully by start of the winter of 2027 will be fully mitigated. I think I'm actually at questions.
Okay. I only see one question in the chat so far, so maybe people can type in more. So sorry, I'm going to go to the question, Jamie. Are you ready?
Yeah.
Okay. So you use INSAR to map movement, right? How do you measure the movement? What software do you use?
We didn't actually use the software. A lot of times you actually have the vendor actually will do the processing for you and give you the results. So we didn't actually do the actual software processing. We had the contractor do that and provide us with the results.
Sorry, trying to unmute myself. I did have a question, Jamie. So on the slide, there was a slide where you showed which drains were functional. I think those are the existing drains. Is that right?
Yes,
Yeah.
exactly.
So did you look into why certain drains weren't functioning, or were you able to determine that?
We weren't able to get into the shafts very easily. So we didn't have access to sort of monitor that, and there weren't records on like which drain was working, which one wasn't per se. And the challenge is that even in the new drains, you would have a work pad and there'd be 8 new drains. One's coming with 10 gallons per minute and the other one's dry. So there's just a huge amount of variability, which is why there's so much probably additional drains that you put in, just because you know that some are going to go really well and some are just going to be duds.
Okay. Another question: how important is advanced testing for geotechnical interpretation?
Yeah, that's an interesting as far as like the exploration, perhaps, as far as understanding the ground conditions. From this landslide standpoint, I think it's pretty critical to understand the slide geometry, that drove the whole layout of the drains. So I guess if I'm interpreting the question correctly, maybe it's because I'm also the engineering geologist. That subsurface investigation is critical to understanding, what we're going to do with this landslide.
Okay. Why not install micropile walls to stabilize the toe in or near the coast?
It's a scale factor. The amount of forces that you're working against with a slide of that size. If you're trying to retain the mass that even for that smaller slide, that's an extreme challenge. There was some discussion about drilled shafts as basically shear piles, but again, it just the amount of force on those, and then Oregon has I think it's goal 18, and basically means that you can't touch the coastline. So that's another restriction that they have, is that really buttressing or even armoring that coastline isn't on the table without a fairly substantial permitting effort.
Okay. Bob, do you have a question? I have another question unless we get more in the chat.
Can you hear me now?
Yeah.
For the final roadway, are they considering doing anything different to allow the landslide to potentially go, but if the roadway was elevated or bridged or something, that it might remain stable and the slide would go beyond it?
Yeah, it's a good question, Bob. We sort of like hypothesized, could you do a tunnel, in behind the mountain, or like say a bridge? In this case, one of the challenges is that you'd have a stable buttress on the south side, but the north side is part of the Arizona in north. So that whole north side is moving as well. It's just not moving as much. So there is just a fundamental concern of no place to land with any sort of structural.
Okay, again, type in the chat if you have a question. I'll ask one in the meantime. Do you expect when you drill the drains, you're going to be able to see that it's productive? And if so, is there any, I guess, potential adjustments?
We do expect to have additional drains put in, kind of field fit. You know, if we don't see anything being produced, or we see a lot being produced, you know, being able to get an extra drain in, or if we have, you know, something that it gets plugged off or for even doesn't work, you know, contractor can go back in. That'll be a little bit more up to the construction engineer for ODOT, and guidance from us, obviously, as well.
Okay. Here's another question. Forgive my unfamiliarity with firsthand landslide mapping experience, but what did you see in the boreholes that indicated shear when initially investigating if you didn't run into bedrock?
That's a super good question. You know, it's really hard in this material. So, you know, it's by definition intentionally sheared and deformed. So, you know, a lot of the decisions as to where the bottom of that landslide were made based off of the inclinometer data. So, in fact, some of the holes they drilled, they just drilled them in. They've done so much work out there. They know it's extremely difficult. So instead of trying to pick apart the sample and make a call, they picked a depth that they felt comfortable getting beneath it, and then, you know, got the inclinometer data to sort of know where that displacement and creep was occurring. Sometimes it's more, you know, if it is a more competent ground that the slide is failing in, you know, you really can pick that out. You can see the landslide debris is deformed or texturally distinct from the intact material, and you can make some pretty good judgment calls. But in this case, you're going from one deformed material to another.
Okay, next question. Do you know of any additional locations in the area where similar landslide issues are evident?
Yeah, you know, so this pretty much from Gold Beach to Port Orford, which is, you know, if you remember the detour maps, those are the two stretches that they're most concerned with maintaining that connection. That whole reach is underlain by basically Franciscan Formation material, and there's, I think, at least a half a dozen landslides that are quote unquote named along that corridor, which basically means they've been there for so long and are so active that they can't fix them, but everybody knows what they are. And there's probably another 24 small slides that are impacting shoulders and things like that. So that whole corridor is really challenging for the DOT to maintain on a good year.
Okay. You're at the end of the questions, but please feel free to type in something else. I will ask Jamie on that. Oh, actually, we got a question. I'll go to that first. Can you comment on the hydraulic conductivity of the geomaterial and how that informed the decision on drains? Also, how was drawdown predicted and related to the factor safety?
Yeah, so two pieces of information that were particularly helpful. So they did do a pump test back in the 90s, and that showed a pretty good response to the you know, the water levels being drawn down by the pump test. So they felt comfortable with sort of at least a big scale permeability being effective initially in the 90s. You know, for us with the effort that we were doing this year, the direction was to not look at other mitigation options, but really focus on drainage just because of access and scale. You know, and we looked less at the hydraulic conductivity of the material and more at the response to drains being installed to sort of assess how much drainage we needed. So if you remember that the the drop and the piezometric pressures, and then the table that sort of showed how much head drop occurred in different piezometers after the initial drain. So we used the guide of the actual ground response to dewatering to sort of say, well, if that's how many drains we need to get 10 foot of drop, we're going to do twice as many to hopefully get twice as much drop.
Okay. Oh, sorry. In your last slide, I think you gave information about the bid period. I don't know, Angelina, if you can back up. Is the link to where contractors can go on there?
It is not, but I don't know if I can get it into the chat. There is a link.
Yeah. Yeah, maybe you can put it in the chat, the webinar chat, perhaps, in case anyone wants to grab that.
So if I am working with ones, if we could like reduce instead of going away from the full screen.
So unshare the screen.
Yeah,
Angelina, can you unshare the screen while he does that?
there we go. Okay, hang on a sec.
We have another question that came in while you do that. I'll wait till you paste it. I don't want to distract you.
Yep.
You ready?
Let's see here. Is that showing up for people?
Yeah, I see it showed up. Thank you. So anyone, any contractors on that are interested in the bid, you can go to that. I think you need an e-bid account.
Yep.
Okay, next question is, what is the use of the SWC curves in the analysis of the landslide?
SWC curves. I'm not sure I know what an SWC curve is. The clarification of that?
It's anonymous. Can that person please type in a clarification? We'll see if that pops in.
Yep.
Soil water characteristic curve.
You know, I don't think we used that in the analysis. It was you know, sort of a traditional limit equilibrium evaluation, and you know, really we focused on, we had a set failure surface and assigned a shear strength based on testing and previous experience, and varied water levels to evaluate the effect of groundwater reduction. So it was a relatively simple analysis, just understanding the complexity of the landslide and not trying to sort of outthink the landslide. We're just looking for basic improvements in the factor safety.
Great, thank you. Okay, looks like we reached the end of the questions. Oh, there's another one. There we go. What are you specifically looking for in whatever software is used to be able to be proactive in preventing landslides when mapping for the mass movement? And what is the name of your dog? Your dog made an appearance in the background.
In the back, yes, she's very popular. That's Nova. She's about 1.5 burner mountain dog, and the Instar is a great tool for, like, if you're doing a corridor study. I would have to say that I was a little this was done before I initially came onto the project, and I was actually fairly impressed with its ability even in vegetated landscape. One of the challenges is that can you get to the ground surface? Are you getting a good response? And it did a good job of sort of at least big scale looking at, is there areas where there's some creep and there's areas where there's nothing going on. So I think that's a good tool. Obviously, LiDAR is an excellent tool from a geomorphic mapping standpoint for looking at sort of regional landslide hazards. And the state highways are great too. That's like a horizontal inclinometer. So everywhere the asphalt's disturbed, you're probably got a landslide. So
Okay, what software was used for the slope stability analysis?
Slide was used for the slope stability analysis by Rock Science.
Okay. I do believe that's the current questions that are asked. Angelina, we're gonna share the last slide, and then if any pop in, we'll ask. So Angelina, do you mind sharing the closeout slide? Okay. So first, thanks everyone for logging in. Hopefully you found it interesting. So when you registered, you could register for free or you could register for a PDH certificate. So the PDH certificates will be available after completed through the webinar evaluation, and you'll get instructions in an email. If you actually signed up for the free version and you've changed your mind and you want to do the PDH, you can email that tech activities at the bottom there to change that, and they can switch it out for you. There's a number of webinars that the various committees in DFI offer. There's more than one a month. So if you go to the DFI website, you will see all the other options. And then also, if you want to give feedback or suggestions, again, I mentioned we're going to do another one next year for our committee. If there's any suggestions related to tunneling or underground, please do let us know. And I'd like to thank Jamie for presenting and being our first presenter for tunneling and underground, and again, the attendees for joining us this morning. And with that, I think we'll conclude.
Thanks everyone for attending.
Thank you.
Have a good day.